Alright, so here is a list of the ways that we've already gone over to factor trinomials. Factoring out the greatest common factor. And if it equals 0, then you can just divide it off and get rid of that greatest common factor. Reverse FOIL, where you try to find two things that multiply to be C and that add to be B. Factoring by grouping. Gary's terrific trick, which comes out of factoring by grouping. And this is when we have an A that's bigger than 1. A difference of squares. And then completing the square is sort of a way of factoring, or using perfect squares to factor. Right. So if you need to use any of these, there should already be a video about this. You can find it somewhere else, or you can just look these up to find out more information. Gary's terrific trick is probably not going to get you many good Google searches, but if you look it up on his website, you should find the video for that. So let's talk about a few additional tricks with factoring. The first one I want to talk about is sort of like the difference of two squares. We're going to call it the difference of two squared. What? So I'll show you what I mean by this. Remember that a difference of two squares is when I have two perfect squares that are subtracted. X squared minus 9. And to factor that, I would just take the square root of each one. Square root of x squared is x. The square root of 9 is 3. And create two terms, one with a plus sign and one with a minus sign. What if I had something that looked a lot like this, but is not actually a perfect square? I can still use this technique to factor those. So for example, if I had x squared, not plus, minus 3. If I had x squared minus 3, yeah, Micah.
And you'd say x plus the square root of 3, and x minus the square root of 3.
Okay, so even though 3 is not technically a perfect square, I can still factor it in this way. Because the square root of 3 times the square root of 3 does equal 3. And so in this way, any number can really be a perfect square. Not a perfect square, because that's not what perfect square means, but any number is a square of its square roots. So let's do one more example. If I had 4x squared minus 5, how could I factor that using this technique?
Put the 4 down. You could do this.
Right. So I'm going to have my two terms. One is going to be plus, one is going to be minus. The first term in each of these is 4x squared square root. So that's 2x. The second term is
5.
But we're going to take the square root of 5, so it's just the square root of 5. That's the only way we would be able to write it. Okay. Kind of a quick way to factor these. Now if I were to be solving for the zeros or something like that, and plug this into the quadratic formula, I would actually get the same answers. This is just a lot faster. It's a quick route to that. Alright. Can I erase this? One other quick trick that we talked about is, I'm going to call it quadratic substitution. I don't know if there's a technical term for this or not.
Quadratic substitution.
This is when I have a problem like this. X to the 4th plus x squared plus, actually let's say 2x squared plus 1. Now, we haven't really learned anything about fourth degree polynomials. But what I can do here is I can say y equals x squared. So I'm just going to take this middle term and I'm going to set that equal to y. That means that y squared is equal to x squared squared, which is x to the fourth.
That only works if the first term.
Right. And since this is my first term, I can use this method now to solve this as if it were a quadratic. And so I'm just going to say y squared plus 2y plus 1. I'm going to factor that by finding what's the word I'm looking for? Factors of 1 that add up to 2. Y plus 1 and y plus 1. In other words, y plus 1 squared. So this is what? What type of factors do I have here? You guys remember? This is a perfect square. Right? My factor squared equals this trinomial. So this is what a perfect square is. Now the last step is just to resubstitute for y. So I have x squared plus 1 squared. And that was my trick when I have bigger, higher degreed polynomials. Right? When I have bigger exponents. Or when I have smaller exponents. So this could also work with a problem like
fractions.
X plus 3x to the 1/2 plus 2. I could do the same technique. If I say x to the 1/2 equals y, so I'm just taking my middle term, then y squared would be x, which is this term. So I would be able to use that same technique to factor this. I would have y squared plus 3y plus 2. My factors would be y plus 2 and y plus 1. And then I would resubstitute. My factors would be x to the 1/2 plus 2 and x to the 1/2 plus 1. That's got a little messy, and we're out of time.